All right, so let's start. So hello, everybody. So we are very excited to kick off the Technical Robotics seminars for this fall semester with Professor Michael Kaess. So Michael has been doing quite amazing work in the wide field of SNAM, single robot, multi-robot SNAM, and personally I was following his works for quite a while, as Michael knows. Let me briefly introduce Michael. So Michael is currently an associate professor in the Robotics Institute at Carnegie Mellon University, CMU. His research focuses on probabilistic methods for robot perception, in particular efficient algorithms for navigation, mapping, and localization. Prior to joining CMU, he was a research scientist and a postdoctoral associate in the computer science and artificial intelligence laboratory known as CCEL at MIT. He received his PhD and master degrees in computer science from Georgia Tech, where our path actually coincided. In 2020, he received the inaugural Robotics Science and Systems Test of Time Award, and he was one of the two runner-ups for the 2012 Walls Dissertation Award for the best US PhD thesis in robotics and automation, and received also, in addition to that, a few runner-up best paper awards at IROS and ICRA. For the past 4 years, he has served as an associate editor for IEEE TRO, and he's currently also an associate editor also for IEEE RAL. All right, with that, Michael, the floor is yours.
Right, thank you very much for the introduction. Let me quickly share my screen here. Okay, can you see my slides?
Yeah.
Okay, great. All right, so today I'm going to talk about factor graphs and robust perception. So I guess I need to introduce really both of these terms before I get started. So here's a quick motivation for robust perception. If we send a rover to a different planet, like here Opportunity on Mars, or the more recent Mars 2020 rover that's currently up there, the challenge is that the communication is really delayed, and that means we cannot easily remote control these rovers, or they're going to make very little progress as we had in the past, right, where it takes a long time to travel anywhere. Because an operator has to be in the loop. So what we really need is that they are more autonomous. And so that requires first that they can actually see the environment, right? So perception is needed, that they need to understand what's around them. We have a similar situation in the underwater domain. Their communication is limited in terms of bandwidth, not in terms of delay. And so that, again, doesn't make it feasible for you to get all the sensor data to actually remote control the vehicle, so it has to be autonomous. Self-driving cars, obviously a very interesting challenge right now. And if you follow the news, just a couple of weeks ago, there was a self-driving car without a safety driver, right? That got to a construction site. There were a few traffic cones, and so the car stopped there. It didn't know what to do. And they had to bring a driver out to actually drive the car around these cones. So obviously, robust perception is still a challenging problem right now. There are some examples where it seems to work quite well, such as drones. One difference is that you can maybe afford a drone to fall down at some point versus a car crashing and killing someone. So this is a slightly different. Where we really want to have robots and autonomy is in indoor environments, service robots. So it would be really nice to have a robot that takes care of the chores in the house that you don't want to do. And you probably saw Amazon's Astro robot announced recently, which is maybe one step in that direction. And so indoor environments, I think, is a very challenging place for robots to operate. So unlike self-driving cars, you can't really have a company come into your home and survey your home. And even if they do that, the home is going to change, especially if you have kids. It will look very different the next day. So the second part of the title relates to factor graphs. So this is more now the theoretical side. This is a graphical model representation that was introduced in 2001 by Xisheng et al. And so the definition out of their paper is a factor graph is a bipartite graph that expresses the structure of a factorization. So it's literally the factorization of a function, for example, probability, density, into individual components. And so here's an example. So it's bipartite. That means there are two types of nodes, right? The circles and the squares. And they represent different parts. So one is the variables that we care about for optimization. The other one is some information that's provided, factors, constraints. And so these factor graphs support a number of different algorithms, especially the sum product algorithm, which then covers many other well-known algorithms, for example, belief propagation, Viterbi algorithm, and more from the robotics side, we're very familiar with Kalman filters, but also other algorithms such as turbocodes that are used in cellular communication and fast Fourier transform. So if we plug this together, factor graphs for robust perception, what we try to solve is we try to solve problems that involve streams of sensor measurements that come from a robot's onboard sensors. And so this might be one or multiple of the sensors that are shown here, camera, depth sensor, LiDAR, typically also including inertial sensors, and then some maybe less common ones like radar that's been used in self-driving cars or in cars in general for safety. And so factor graphs in this context are useful for three different things. Number one is modeling the typical inference problem that we encounter in this context, and I'll show some example shortly. Number two, they can be used to perform inference itself. So we have algorithms such as the belief propagation before that allow us to solve these inference problems. And then the third one that we found particularly useful is that it's a really good tool for developing new inference algorithms that are specific to the structure of the problem that you're facing. So if you look at one example of a perception problem in robotics, it is SLAM, simultaneous localization and mapping. So the problem of a robot starting in a new environment, a new home that it just got unpacked in, and it now needs to map that environment, but at the same time, it needs to localize itself with that map that it's building. So the robot would take its sensors and see what's in the environment. So here it's observing a chair. More traditionally, this might simply be point features that are extracted from camera images. The key is that they have some kind of measurement, landmark measurement, that of that observation. So for the chair, this would be a relative pose. So what's the relative orientation of that object and the relative translation. For a point feature, it might simply be the pixel location in an image. Now the robot is moving through the environment. We get an odometry measurement. So the odometry could be wheel odometry, so wheel encoders telling you how far the robot moved. It could also be from other sensors, visual odometry, LiDAR odometry, and inertial sensor. And then from the new location, we're re-observing that previous chair, and maybe we now see another object, a table here. So where it really gets interesting is if the robot is driving for a while through the environment. Let's say it's a bigger building, and you're exploring this building. And the problem is that all of these measurements are uncertain. And so these small errors that you make in measurements, even if you use a laser rangefinder, and it's still the range measurements are off by millimeters at least, the drift, the errors accumulate, and that translates into your state estimate and your map being off from the correct solution. So this is called drift. And so that drift accumulates over time. So if the robot now comes back to a location it's previously observed, so for example, it gets back into that room where the table is, and let's say it can recognize it's the same table, then we can incorporate what we call a loop closure measurement It's simply, again, a landmark measurement as before. But the key difference is that in this case, it will significantly disagree with the current state of the robot. Right? According to the current state of the robot, that table should be 20 meters away in a different location. But according to the landmark measurement, it's only 2 meters away from the robot. So we can use that loop closure measurement to now correct the state of the robot, like where the robot is relative to that table. And with that, we can also correct the complete trajectory backwards that the robot went through the building. And we can correct the map, so all of the objects it saw on the way. And so the more of these measurements we get, the more accurate the map will become over time. So how do we do that correction? And for this, we go to a factor graph representation of the problem. So same as before, but instead of showing a robot here, we now have a node that is an actual variable that contains the robot's pose. And so in a 2D example, this would be the XY position and orientation yaw. Typically, we do this in 3 dimensions. The landmark's position can be XY, or if it's a chair, like before, it would actually have an orientation also. And then these small black dots in the middle are factors. So they are measurement, they correspond to measurements. So the landmark and odometry measurements. And so together, this is this bipartite structure where some of the nodes are given and some of the nodes are the quantities that we want to estimate. And so these are variable nodes and factor nodes. And in this bipartite graph, the edges will always connect from one variable node to one factor node. So this means if we look here, there isn't a single edge that goes through across this M1. It's actually 2 edges. One goes from X0 to M1, the other one from L1 to M1. So this allows for things like these monocular unary factor that connects to a single variable, right, P. This is some prior here that constrains a coordinate frame. It could be a GPS measurement if you're outdoors. These here are binary constraints, but there are also higher order constraints possible. For example, if you have calibration variables, if you include a calibration of cameras into this optimization problem. So beyond the SLAM problem, there are actually many different problems that we can formulate as a factor graph. Essentially every optimization problem you could formulate this way. So here are some examples. Tracking, for example, the position of an object, what typically would be done with a Kalman filter or extended Kalman filter. We can model this as a factor graph here, where at different times we can model the position or the position and orientation of that object. There are other like switching systems. Optimal control is interesting. So here we actually include the control parameters as variables. So we can optimize over those and figure out what the control should be. The SLAM problem we just discussed, so these are poses and landmarks. A variation of this is post-graph SLAM. So in this case, we have no landmarks. We only model the position and orientation of the robot at different times. And the measurements here are derived maybe from observing landmarks. So for example, from visual odometry. So we essentially marginalize out landmarks to get these relative constraints, either between sequential poses, that could also be real odometry, inertial, or in this case here, a loop closing. So this would be from aligning some sensor data, like 2 camera images and figuring out the relative transform between these. And then this is also closely related to structure for motion and computer vision. In fact, this looks very similar to the SLAM problem. The only difference is that in structure for motion, you're given a couple of camera images, but you don't know their relation, so you don't have odometry between those. So in some way, the SLAM problem is really a generalization of structure for motion, where we might have different sensors and different kinds of measurements in addition to just observations of point features from a camera. Okay, so after this, quick introduction, I want to give an overview of factor graphs and Gaussian inference. So how do we solve optimization problems that are formulated as factor graphs? After that, I'm going to talk about problems in the current formulations that make it difficult to achieve robust perception at the moment. And this relates to some assumption about Gaussian noise distribution or Gaussian densities that's inherent in current solvers. And then I will conclude. All right, so let me start with a simple example of what goes into a factor graph to make a bit more sense out of this. So here's a very simple example where we have a robot observing a landmark in 2D. So what we want to figure out is, for that one observation, how would a factor look like? What would be the math inside? So we have that robot in some wall coordinate frame given by xy. So it has position rx, ry, and some orientation r theta. It's observing a landmark. That landmark is also specified in the wall coordinate frame as lx, ly. But what the robot is really observing with its onboard sensors is a relative position of that landmark. So a zx, zy position in the robot's own coordinate frame. Right. So if we write down what the measurement is that the robot would see, if we knew exactly the robot's location and the landmark's location, then we can calculate just by subtracting the robot's origin from the landmark's position and rotating it into the robot's frame, we can calculate what the robot sensor would observe here. But of course, a real sensor is noisy. So the generative sensor model here, with the assumption of Gaussian noise, is that the sensor measurement will be exactly this prediction. If we know the ground truth, if we know exactly what the robot is and the landmark is, plus some noise, zero mean Gaussian noise, with some covariance psi here. And so with this, we can now calculate the probability of a measurement. Right? So what's the probability of that measurement z given some R and L? Right? R and L is actually what we try to optimize over later, right? We don't know that. And Z is actually given. So this is kind of the opposite way. But this is needed in the optimization to figure out what R and L is. And so this is simply a multivariate Gaussian density that uses the prediction HRL, subtracts the actual measurement that we got from the sensor, and then we apply this Mahalanobis distance that takes into account the uncertainty of that specific sensor. And so this assigns a probability, but equivalently, we can look at the cost. So instead of maximizing probabilities later, we can minimizing costs. So we can just look at the exponent here of the Gaussian density, and this would be that Mahalanobis distance. Okay, so this is what goes into a single factor. And let's see, now if we have a factor graph with lots of these factors, we can write a factor graph as a factorization of a probability density, where these individual factors are exactly what we just looked at. These would be these multivariate Gaussian densities, each one having their own H function depending on the specific sensor that's being used. Theta in this case represents all the variables. So these would be the poses and landmarks in this specific case. And now what we really want to find is we want to find the poses and landmarks that maximize that probability, or in other words, that best explain all of the sensor data, all of the Z's. Under Gaussian noise assumption, this simplifies to minimizing a sum of square differences, or actually Mahalanobis distances here with xi in it. And so there's a typical least squares problem. And so that's the reason why Gaussian densities are chosen. This simplifies the math significantly. And this will be a shortcoming that we'll look at later. So again, we have this generative sensor model in here, the actual measurement and the uncertainty, and that's all. So now again, we would find a theta that minimizes the sum of squares of these errors. If we further assume that h is a linear function, which is typically not the case, but we can linearize h if it is not, and we can have an iterative algorithm that starts with an initial estimate, linearizes, gets a new estimate, and then linearizes at that point again until convergence. So this would be algorithms like Gauss-Newton, Leonberg-Marquardt, or Powell-Stockyak that are typically used here. So now we're down to solving a linear least squares problem, which is simply some large matrix A times that vector of variables theta minus B, which is another large vector. And so now the question is, how do we solve this efficiently? Because we have to solve this many times over and for very large numbers of variables theta. And so the key insight here is that that matrix A is actually sparse, and that sparsity relates to the structure of the factor graph. In fact, each row in this matrix corresponds to one factor. And so a factor connects only to a small number of variables, often 2. So this means in a row here, there are typically only 2 blocks or 2 entries or blocks of entries. So the columns of this matrix is made up from the variables. So in this case, poses and then landmarks. And so that means if you look at this diagonal line here, what this actually is are the odometry measurements. So in each row, if we would zoom in here, there are 2 blocks that connect sequential poses. And these measurements are the landmark measurements. So we have 1 pose and 1 landmark in each row. So as you can see, there's a very sparse matrix. And so this allows for efficient solutions. So brief history of algorithms that we developed in this space. We call this smoothing and mapping. Smoothing as opposed to filtering. So not using a Kalman filter, but solving a full optimization problem over the structure, which gives better results. And if you do it the right way, right, it can actually be done efficiently. At times even more efficient than a Kalman filter, because you can exploit that sparsity. So the first one was square root SEM. So this is batch solving, exploiting the sparse structure. And so here, my thesis advisor, Frank Dillard, had the key insight of using ways how bundle adjustment structure for motion is solved in computer vision to apply this to the robotics problem. And so then you can do sparse matrix factorization to solve. And so this recently got us the RSS Test of Time award in 2020. So based on that, this is exploiting the structure that's in the problem, so that the factor graph represents. But that factor graph is growing over time. So there's also a temporal structure. Instead of resolving that same problem over and over with just a few measurements added, we can actually incrementally update it. And so this is ISEM, incremental SEM. So in this case, we do incrementally updating a matrix factorization, which is also kind of well known how to do this. And so this was my PhD thesis. The key, so if you have a matrix factorization, you get some new measurements. You can essentially calculate the updated matrix factorization by just recalculating a couple entries shown in red here. And this is the same as if you would have batch factorized this whole matrix again. Of course, that saves a lot of computation typically. Now, the restriction is we're working with matrices. They're actually linearizations of the nonlinear system. So the question is how to incrementally update a nonlinear system. And this is later work that we did, so-called ISEM2. And for this, we went away from matrices. We basically looked at how does that inference work if we think in terms of graphical models. And so when we try to figure out what is sparse matrix factorization in terms of graphical models, we had to introduce a new graphical model that we call the base tree, that's shown on the right here. And so with that, we can then define a new algorithm that incrementally updates a nonlinear least squares problem. And so that's the central algorithm in the GTSAM library. So that's actually freely available if you want to play with it. All right, the key insight or the key algorithm that's behind that is variable elimination, something that's also well known in the literature. So here I will explain this for a very simple example with only two variables and two factors. So we have x1, x2, robot poses, let's say, and then we have this unary factor at the beginning. It might be a GPS measurement at the first pose, and then we have this odometry measurement. There might be visual odometry between x1 and x2. So these correspond to two factors or two functions that we can think of probability densities that you can multiply together. And so variable elimination is changing this by eliminating one variable at a time to convert this graph into something else where we can do inference on. And that conversion, if we eliminate x1, we are essentially taking all the factors connected to x1. So these are both factors in this case. And we are writing it in terms of a conditional on x1 that is being eliminated and some potential on the remaining variables that were connected to it. So in this case, we end up with this conditional probability density x1 given x2, and then some additional new factor on x2 that contains essentially the information on x2 after marginalizing out x1. So this notation is a bit strange. It combines a base net and a factor graph. You could write this as two different graphs, but for convenience, we can also combine it. So if we do one more step, eliminate the second variable, we end up with just the base net. And so that base net has two components in it, two probability densities. And so now, since we have a probability density just on x2, we can actually solve for x2. And so in the solving steps, we just go backwards in reverse elimination order. We solve for x2. We can now plug x2 into this conditional x1 given x2, where that means there's only one variable left again. And that means we can solve for x1. And so this means now we have a solution to this optimization problem. So that's the basic idea. It gets a bit more complicated if this graph is not a chain, so if there are loops in it. And it also gets more complicated if these underlying pieces are actually nonlinear functions. But other than that, that's really the key of the algorithm. So we can take this a bit further. We look at a chain of poses to implement a fixed leg smoother. So in a fixed leg smoother, we want to keep the last n poses, and we throw away everything that came before that. Or we're actually not throwing it away, we're marginalizing it out, so we keep the information from there. So the way this looks like is, let's say we already incorporated 4 different poses and we eliminated them. So we end up with this eliminated base net that consists of 3 conditionals and then 1 prior on x4. So now we can simply drop x1 because that is equivalent to marginalization, right? The elimination already did marginalization. This is one side effect of elimination, but it also gives us the conditionals that allow us to solve later. Okay, so dropping that corresponds to marginalization. So now we have a fixed leg of 3, so we keep 3 poses around. Now the question is, what happens if we get new measurements? New measurements mean where the new time step, the robot has moved, so we add a new variable x5. And let's say we get an odometry measurement in red. We get a new GPS measurement, let's say, in red here. What we additionally have to do, remember, let me go back quickly, remember the this P, actually this here, this P of x2 here. This doesn't show up in the base net, but we now have to get it back. We have to create a factor out of it. We can simply convert it back into a factor. And that allows us to restart the elimination at x4. So we don't have to go back to all the raw measurements and eliminate from x1. We can simply restart at x4. So we do variable elimination. That gives us that conditional and that additional probability on x5 that doesn't show up in the base net. And now we have, again, a fully eliminated base net. We basically did inference over this whole chain without recomputing all the previous information. So we have updated this fixed leg smoother. And we can simply drop x2 now. That corresponds to marginalization. So now one interesting question. What is a fixed leg smoother with lag of 1? So if we only keep the most recent pose in the fixed leg smoother. So that's actually something you all know. That is a Kalman filter. So in a Kalman filter, we always marginalize out the oldest, the previous state, and we only keep the most recent one. Right. So this is simply a generalization of the Kalman filter in the linear case. If these factors are nonlinear, then we can actually do relinearization, something that the extended Kalman filter cannot do. And that's because we keep some of the older states around. So that means we can still change linearization points and relinearize measurements with some restrictions. So for example, you cannot, for the oldest state, you cannot because it's connected to something that is marginalized out. And that's actually what causes problems in the Kalman filter and what causes inconsistency if you apply the Kalman filter to the SLAM problem. Okay, so now we can go a step further and do incremental nonlinear least squares. That's essentially updating now a tree structure. Incrementally, you can see the red entries here is what changes in every step. These are often local changes near the top of that, the root of the tree. On the right, you can see the map that's being created. That's a robot driving through a Manhattan world, and there are loop closures. So it's a post graph that's being optimized here. And you can see that these changes are often very local, but sometimes if there are loop closures, then of course all of the variables that are included in this loop closure along that loop have to be re-optimized. And so this means you can see bigger parts of the tree popping up in red. So most of the time we save a lot of computation. Sometimes we have to do more computations up to the point of a batch optimization. So for example, in this graph, you can also see the cost in color. So yellow to red. Red means a lot of variables changed at this point. Yellow, some, and green is a small number. So it's mostly green, but as we revisit areas here and stay in the same area, it becomes more expensive. And now there's going to be a big loop closure up here. That point is really expensive, and you saw the whole tree popping up in red. Actually multiple times because of relinearization also. Now we're exploring a new area. And again, this is cheap because for mapping this new area, you don't have to revisit the old one. In fact, you get no new information about the previously mapped area. Okay, so this can be used in a number of different ways, and I'm going to show a couple of applications here. So one is visual inertial navigation. At the bottom, you see there's actually Kalman filter-based solution we did at the time, which you can walk through a building. You have a camera and an IMU together. You track feature points, and you combine this with inertial sensor data. You can calibrate inertial sensor on the fly, and you can help the camera if it loses track of features. And so with this, we can track the position of a person walking through the building here. And at the end, we are a bit off by 1 or 2 meters. So there's some drift in that if we don't incorporate loop closure. So this is not SLAM yet. And so going back, actually, Vadim back in 2013 figured out how to do this, not in a Kalman filter, but in a smoothing framework using ISM2. And since then, there have been a lot of iterations of that work, and this is kind of the state of the art nowadays, to incorporate this within not necessarily ISM2, but within a fixed leg smoother instead of a Kalman filter. There are also other things you can do with that. For example, you can parallelize smoothing and filtering within the space tree structure. So we can have something that runs fast, the filtering portion, which could be a fixed leg smoother itself. And then we have something in the background where you incorporate the loop closures where the computation will take longer time. But both of these are part of the same tree. Visual inertial odometry, more recent development. So something we did a couple of years ago. This is on a quadrotor now, flying in real time. It's actually used to control the quadrotor. See the camera images, you see the inertial sensor measurements. And so from this, we can calculate the trajectory of the vehicle, the velocity, which is important for control. And the key contribution at this point, now it's really doing refinements of these algorithms, was that we found a way to preserve consistency by not randomly throwing away some information or duplicating some information, but by actually performing a sparsification on that graph to keep it sparse over time, and also keep it a conservative estimate. And overall, that's a consistent estimator then that outperforms the state of the art in that. More recently, we combined this with multiple cameras. So if we have cameras looking in different directions, that increases robustness. Robustness is one place I want to go here. So this can overcome motion blur to some degree, right? If one camera is close to the surface and things move fast, or if there's no texture in that direction, if you're looking at the textureless wall, then hopefully the other cameras can still see something. And so you can do a combined optimization over both. This is using a joint 1-point RANSAC, so it's actually very efficient. So it did turn out that you actually have to take the extrinsic uncertainty into account. So you need to know the calibration between these sensors and their uncertainty also to make this work well. And yeah, so with that, in a bit challenging environment, moving fast, we get a good trajectory, while the system with just using one stereo camera actually fails and gives us a trajectory that doesn't align with the map here. Other examples, so some other work we do is on underwater robotics. So there we have to use sonar sensors to, since with cameras you cannot see far, lasers also don't go far into water. And so with sonar sensors, they're a bit like cameras. Imaging sonar is a projection of the scene. So you're losing some information. With the camera, you're losing the range information. So you get the X and Y coordinate, but not the Z. With a sonar, you're getting the range information and the X coordinate, but not the Y direction. So you're losing elevation. And but if you have multiple views, similar to structure for motion in computer vision, we can recover the 3D of the scene and also where the cameras were located. And so that's what I call acoustic structure for motion. The geometry is a bit different, but you can still formulate this as a factor graph and either localize point features that you observe, like these point features on a ladder on the water in a harbor environment, or you can, and that's the more interesting part, you can actually localize the vehicle with that. We've also recently looked at expanding this optimization to incorporate inequalities or equality constraints. So the typical formulation is simply a least squares problem unconstrained. But in some places like manipulation, you actually have constraints because you're in touch of some object. And so you can now incorporate this in the graph. This can also be used in the mapping context, or if you have a map available, because you know that the vehicle cannot go through a wall. So you can use inequalities for that. This increases the complexity of the optimization. It's some primal dual problem that has to be solved rather than just the least squares problem. Other people in this field have also used these algorithms to solve a novel problem. So for example, attacking the planning problem. This is by Frank Dillard and Byron Boots. The simultaneous trajectory estimation and planning. So in this case, we're looking at this factor graph as having both the history, which is the SLAM problem, and the future, which is the planning problem in one. And we can then optimize over that to figure out what the robot should do next. Another example from another group is on robust sensor fusion. So we can incorporate into the factor graph other variables that contain, in this case, parameters of Gaussian mixture densities. And so with this, these parameters can automatically be optimized, which is used for robust sensor fusion. Yet another example is on learning semantic maps. So in this case, we have discrete variables in the factor graph that correspond to certain locations, for example, or actions of or relative positions between locations and objects. In this case, of course, the optimization becomes a bit more tricky because we now have discrete variables in there, and we have to do that somewhat differently from what I've explained so far. And then the last one on occupancy grid mapping. Here, the authors revisited a kind of old problem of how to create occupancy grids, for example, from laser data. And instead of just having this each occupancy cell independent of each other, they are actually looking at relations between neighboring cells and encoding this in the factor graph, and this can still be efficiently solved. Okay, so after this overview of different methods to solve such problems and also examples of what you can solve with that, I now want to address a problem of these methods, and that's robustness. So we want to look beyond this Gaussian assumption. So let me start with some motivation for robust perception. So why do we even have a problem with robustness? The issue is that there are some failure causes, such as perceptual aliasing. You can see here, there are two corridors shown that on the first view actually look to be the same. But if you look in more detail, you can see the signs up here are slightly different. So this indicates there's actually a different corridor in the same building, maybe next to each other, parallel to each other, or on different floors. So if you, yes.
This is the Ulmer building in the Technion. These are the floors from the Ulmer building.
Okay, perfect. So I used the right images here, so you're familiar with the. Is it actually different floors, or is it on the same floor?
Actually, they are two different floors. Yes.
Okay, different floors. Good. Yeah. So as I mentioned earlier, right, if the robot is going through a building for a while, right, we have drift accumulating. You're now coming back to a location that you think that looks the same as before. But if you now incorporate this constraint and it turns out it's not the same location, this will lead to catastrophic failure. So here's an example of a map by Ed Olson, from Ed Olson's paper, where there's a wrong loop closure being inserted. The first one actually doesn't do a lot of harm here because we have a pretty consistent, lots of measurements in this map already. But if you add a few more wrong loop closures, then you see that that map actually, just with 3 wrong ones, that map becomes pretty poor, not a good description of the environment anymore. And if you have a few more, it's completely useless. So this is one consequence of that Gaussian noise assumption. It basically cannot accommodate for outliers. There are other examples where failures can come from, such as wheel slip. So if your Mars rover is reporting, the wheel encoders are reporting that it's moved 10 meters forward, but the wheels were actually slipping in the sand, right? And it just moved a meter forward. That's a problem if you don't model this correctly. And with a Gaussian density, this is difficult to model. Sensor failures, this is maybe a bit less common. It's more that environmental conditions, such as the sun shining into your camera, right? And your camera image becomes difficult to use, or a laser hitting a mirror, for example. So it's not really the sensor failing, it's data that you simply don't expect and that you haven't modeled. And finally, nonlinear functions that underlie most of the sensor measurements that we get actually lead to non-Gaussian posterior densities. So even if the measurement uncertainties are Gaussian, the posterior, so the state that the state estimate for the robot cannot be well described by a Gaussian density. And this is, for example, true if we look at mapping using range information, for example, from sonar. We then end up with these bimodal distributions or uniform distributions over some interval that are really difficult to or not well described by any Gaussian density. So the question is, how do we solve these problems in the back end, in the optimization? So the back end is one part of a typical SLAM system. There's a front end, which is what's processing the sensor data. And of course, at that point, we can do a lot about robustness. And but the focus here is going to be on the optimization. So on the front end side, right, there are a lot of complementary approaches. For example, instead of just point features, we typically would use feature descriptors. That makes it much more robust to match features with respect to each other. So if you use a SIFT descriptor, right, most of your correspondences are probably already correct that you find. You can find correspondences then also using deep learning methods, recent methods such as SuperCLUE, that are relatively robust and get rid of outliers. Of course, traditional methods, RANSAC and so are also in use here. And you can even go further. You can look at consistency over multiple time steps. So you don't just believe that this is a loop closure right now. You're basically moving on into the next room and looking, oh, does this also agree? And then you incorporate all of these constraints if they agree. So one example is the pairwise consistent measurement set maximization by Josh Mengelson. And another one is robust loop closing for postgraphs by Yasser Latif. So all of these methods are really helpful in robustness, but at some point they still make a mistake, right? And at that point, it's up to the optimization to fix it. And right now, the optimization typically also fails at that point. So here is an example of ambiguity. A situation where a robot is observing two doors in an environment. This is very simplified, but let's say there's a camera with a door detector. You see the two doors, and then you create a map essentially of that, you know their location. Now you're moving forward, and the noisy odometry of this robot tells us we have moved 1 meter forward. Now, if we look at that new location, we're actually seeing two doors again. So one possibility is that the robot only moved 0.5 meter forward. This is based on the observations of where these doors are. Or that the robot moved 1.5 meters forward, and we're actually seeing the second door and a new door that we haven't seen before. So to model such a situation, we can incorporate a multimode factor in the factor graph. So that's a factor that has two different options. There's essentially a discrete variable here that decides is it one or the other, but we marginalized out that discrete variable. And so what remains is this multimode factor. And so there are a couple of different situations that typically pop up. One is this multi-measurement. It's one or the other. Right? This could be wheel slip, right? There's one Gaussian that describes wheel slip and another Gaussian that describes the normal situation. Multi-association. So in this case, we're seeing this table, or it's a new table that we haven't seen before. Right? So either the green one on the left or the green one on the right. And then Boolean. So here we have a loop closure. It's the same hallway, the same place we've been before, or it is not. Right. So the problem is, how do we solve this? Right. Clearly, the posterior of this inference problem is no longer Gaussian density and cannot be described by a Gaussian density. So we have to do something different. A typical solution is to use robust estimators. So robust estimators are good at getting rid of outliers, right? So wrong loop closure measurement. Let me quickly explain this. So if we take a Gaussian density here, that corresponds to a quadratic cost function. So if you have an outlier here, so something that's far from the mean, this quadratic cost will be really enormous, right? It will be a high cost. And so if this is one of the terms in the sum of squares, And so the optimizer will now try to get that down by moving all of the other cost terms away from their optimum. So this is why the map degenerates, why the map looks terrible after incorporating some wrong loop closure. And so the idea is to modify that function to only be quadratic near the minimum, and then, for example, become linear if you go away from the minimum. So now the penalty is much lower. There's still a penalty. There will still be a bit of an impact of outliers, but it's not catastrophic as in the quadratic case. And there are a couple of different of these functions around. There's actually a recent paper on adaptive robust kernels that's essentially blending between a whole family of these functions and automatically learning which of one is the right one to use in a certain situation. There are also other solutions, such as max mixtures, that have been proposed. So max mixtures is just doing a normal least squares optimization, but locally makes some decisions of which of these two modes to pick. Obviously, this can get stuck in local minima, so it depends on what these measurements describe, if this can be locally resolved or not. Switchable constraints is another such idea, where we have a discrete variable in the graph that decides, is this loop closure here between x2 and xi on or not? And to incorporate this in the optimization framework, it's actually implemented as a continuous variable. So it's kind of a soft switch of the two. And now you can still do least squares optimization. Another possibility is to have a global solver for postgraphs. So recently from MIT, there have been a series of papers that looked at semi-definite relaxations of postgraph optimization problems. So this only applies to postgraphs under some assumptions on the noise that are pretty realistic. And at that point, you can actually find the global minimum. And you can even potentially certify that you have found the global minimum. But there are some restrictions, right, in terms of what optimization problems you can solve. So everything has to be relative poses. Another possibility, and so this is still Gaussian at the end, so everything has to be Gaussian. Another possibility is to go away from Gaussians and do inference with arbitrary distributions. Now, there are no good efficient ways of doing this. One way is to do non-parametric belief propagation, so there's sampling involved, so kernel density estimates for the underlying distributions. And that can be combined with the base tree structure for efficiency, but it's still very expensive to do. So this is not something we can do in real time, and it's also proximate. The problem is that the underlying optimization problem is simply intractable. So we then went back to an old idea to get to a real-time system. And the idea here is multi-hypothesis tracking. So for the special situation where you have multiple discrete possible solutions, right? So loop closure on or not, you see this landmark or that. But each of these solutions is actually can be modeled with a Gaussian again. Then we can go back and simply have a different solver for each of the different hypotheses. So in this example here, we have 6 different bimodal factors. And so that yields 2 to the 6 or 64 different hypotheses. So that's a problem, right? There's an exponential growth in here. And so this requires pruning as typical in multi-hypothesis tracking. The difference to typical multi-hypothesis tracking is that our state space is not 3 or 6 dimensional, right? Where you can easily have multiple filters running in parallel, but you have these huge systems, right? That you can maybe afford to only run 10 of these in parallel. So we have to do a lot of pruning and prune out the ones that are least likely, but it could be that the correct one is included. So with this, we can explore some overlapping computations, and we can actually simplify the problem a bit, save computation. The different hypotheses share some common computations. And so it turns out we can actually represent all of this in a single base tree, where some of the cliques have multiple hypotheses, others might only have one hypothesis. And so this saves some of the computation. With this, we can solve problems like here. We have a robot going through an environment, and you can see in light blue the ground truth, solution. So no ambiguity included there, just solved. In blue to magenta, you see different hypotheses. So in this case here, there are two hypotheses, the blue one, which is the correct one, and then the magenta one, which is off. As the robot moves on, there are actually more hypotheses. So now we have at least 4 here that I can see. And at the end of this, there's actually only one left. You have enough measurements that you could disambiguate. So if you solve this problem, you can actually apply other methods and they will work and we get the right solution. The problem is the robot has to get these intermediate solutions, and that's where the failure happens. You do not have enough information to make that decision. If you pick the best one locally, you end up with a red trajectory, which is completely wrong. So if you keep track of these multiple hypotheses, you know that there's ambiguity and you can recover from that if you don't throw out the correct one by pruning. Here's another example, Victoria Park dataset, unknown data association or ambiguous data association. What I need to point out is that the theoretical number of modes here is huge, right? 2 to the 400. This actually vastly exceeds the number of atoms in the universe. So that's why intractable, there's no way to calculate all of these. Let me, in the interest of time, maybe I jump very quickly over this here. Previously, my PhD student, Ming Xiao, did mapping using planar surfaces. So in an environment, you can just look at planar surfaces. This works well with stairs. It's a bit more tricky. In a corridor, you might not see 3 different planes that you need to constrain. So we combine this with inertial sensing, also enforce structural constraints, orthogonality, and we can generate pretty good maps. But if we are not careful how we move the sensor, things fail, right? We get wrong loop closures, we get wrong constraints in between. And so here on the right side, you can see maps that were generated with the usual approach. On the left side, this actually motivated this whole approach of multiple hypotheses. You can see the maps solved using multi-hypothesis tracking. And the top one looks wrong also, but it's actually 3 different maps overlaid on each other. And so one of them is correct, the other 2 are not. And later on, this will become clear as the robot moves on and there's disambiguation. But if you make that decision early on, then you end up with something wrong at the end. Similar for this larger map that already has almost no ambiguity left. So, and with this, we can also do active disambiguation. If we know the ambiguities at a given time, we can have the planner incorporate that information to try to keep the number of hypotheses bounded. And if we can achieve that, then we don't have to do pruning and we don't risk that that we throw out the correct hypothesis accidentally. And so let me jump over this quickly. So in conclusion here, what I hope that I've shown today is that factor graphs are a very useful tool for modeling many robotics problems, so beyond SLAM. That it's also a very useful tool to understand and create new inference algorithms. So for example, we can understand the fixed leg smoother related to Kalman filter. We can design new algorithms such as ISM2. I hopefully also convey that robust perception is hard. Right? Generally, it's actually intractable because of these discrete parts in there that lead to exponential growth. But you can still find some limited solutions, right? They will always have the problem that it might fail, but in practical situations, most of the time, hopefully they will work. We can use robust estimators. We can do global post-curve optimization, finding a global minimum. There's non-parametric belief propagation to get an approximate solution for completely non-Gaussian problems. And then finally, multi-hypothesis if each of the hypotheses can be well described by a Gaussian again. What I think is still an open problem that also needs to be explored more is how do we use that knowledge of ambiguity then for planning? So how do we incorporate that and trade off between the task that the robot needs to do and the revisiting of previous places that helps us with this ambiguation. All right, so with this, I want to end with a quick acknowledgement of funding. So a number of government agencies and companies that funded my research over the past 8 years at CMU, and my collaborators, colleagues at CMU and at other universities, MIT, Michigan, Georgia Tech, Maynooth, and Brigham Young University. And then, of course, the many great students over the years that made this work possible. All right, so
Thanks
I'm
a lot,
happy to answer questions.
Thanks a lot, Michael, for this amazing talk. It was very interesting, in my view, at least. Okay, we have some time for questions. Anybody here in the audience want to ask? Now is the time.
So there's a question, a good course or book on factor graphs. Let me quickly. So in terms of resources, and I think you already know that one at least, and I can maybe get back with something else. But in general, the factor graphs for robot perception is some overview that we wrote a couple of years ago now that I think provides an introduction to the problem and an overview of the different algorithms and also applications. That is a good starting point. And if you want to play with this, the GTSAM library actually has the ISM2 algorithm and other algorithms that are useful.
And you, Michael, also has another version of multimodal ISM available?
Yes, there's actually also open source. It's unfortunately not in the GTSAM library at the moment, so but it's separately available. It's using an older version of GTSAM, so there's some work we need to do there.
Cool.
Oh yeah, this is the multi-hypothesis one. There's also the multimodal, the non-Gaussian version, which from MIT is available. It's available in a different programming language, Julia. So that's by Dehan Fourie.
Very nice. Anyone wants to ask a question, maybe? So, Michael, maybe I'll ask a quick question about ambiguity. Where do you see the challenges there now? People are working on this nowadays.
So I think coming up with better inference algorithms is certainly one. So multi-hypothesis is one way to approach it, but it's still somewhat limiting. If the ambiguities are Gaussian, right, we can maybe deal with it. But often what we see is that that underlying distributions are not necessarily Gaussian in the first place, and there really isn't a good solution to deal with these. The Hans work is closest to it. So the question is, are there better ways of sampling from distributions of doing this inference that could speed this up significantly? There's actually a recent work also from MIT with Dehan involved as a co-author that applied learning in this context to try to do the sampling in a better way. So there is work in this space, yeah.
The neural flows, the normalized flows.
Yeah, correct.
Very cool. Right, I think in the interest of time, I think we should finish now. So Michael, thank you very much for this interesting talk.
Yeah, thanks for inviting me.
It's been a pleasure. Thank you. And we'll meet again next week for the next speaker. Thank you all for attending. Thanks. Bye for now.
Thank you very much.
Thank you.
Thanks.